So we're going to continue with example F, trying to find the volume of a solid of rotation, a sailor. In the last example here, you were asking me why I did this minus this, which is really your x-coordinate, right minus left. The x-coordinate here was y, 1/4 y equals x. But I took the time to write right minus left, this minus 0, or this minus 0. And the reason for that is because you're not always going to be rotating around the x-axis. So in order to correctly calculate the radius, you have to do top minus bottom or right minus left, whatever the case may be. So to illustrate that, instead of rotating around the x-axis, let's rotate around the line y equals 2. So we're going to change our axis of rotations for this next problem, just to give you something a little bit different and make sure that you're prepared in case you get something like this in your homework. So this is our axis of rotation. Now, is this figure flush with our axis of rotation? In other words, are we going to get a disc or a washer when we rotate this around the line y equals 2 and take our little perpendicular slice? Yeah, you're going to get a washer because there's a gap between your figure, between your area, and the axis of rotation. So let me sketch this in here, like that. That's going to be our slice, and it's going to result in a washer. So let's work on finding the volume of one washer. Volume of one washer. Now we'll kind of jump up a little bit based on our work last time. And I'm going to write that volume equals pi times R2 squared minus R1 squared. And this time it's going to be a dx slice. Let me give myself a somewhat generous washer here. So you're going to have two radius. You have an inside radius and an outside radius. The inside radius I'll call R1. The outside radius is going to be R2. Let's think about which one's going to be which. We'll have a radius here and another one here. Which one of these, the bigger one or the smaller one, is going to be R1? Smaller one, it's going to be R1. This will be R2. I need to find the length of each radius, that is the distance between that and this axis, for both R1 and R2. Now, because we're working with something in the vertical direction, it's going to be top minus bottom. So let's take a look at what that's going to be for R2. R2, top minus bottom. Top is just going to be the y coordinate here. So the y coordinate is, just y, but if we're going to write things in terms of x, instead of using y, I'll write 7 minus x squared. 7 minus x squared minus the bottom. Well, the bottom in this case is no longer just 0. It's 2. Cleaning that up, that's going to be 5 minus x squared. So that's my larger radius, my outer radius. I got to do likewise for the inner radius. So I need R1. Again, it's going to be top minus bottom. This time you should end up with a little bit easier expression. So give yourself a chance to find that. What's the expression going to be I'm going to use to calculate R1? Well, it's just going to be this distance here. This is the line y equals 3 that's given to us right here. And we can read it off of the graph. So there's your y equals 3. So it's going to be top minus bottom, so it's going to be 3 minus 2, which is just 1. And that's okay. You know, it doesn't bother me if we get a nice, easy part of our problem here. But that's what we needed. And so that's why I was always in the habit of taking this slice and doing top minus bottom and left minus right, is because sometimes these bottom numbers or the left number, the second one, isn't always just a 0. So we've got to be careful with that. Let's put this in now and figure out the volume of one washer. So volume of one washer is going to be a pi times 5 minus x squared squared again minus 1 squared times dx. Now do me a favor. When you square this out, don't just give me 25 plus x to the 4th. Something a little bit more to it than that. If you need to, take an extra sheet of paper and kind of write that on the side. So you can do 5 minus x squared times 5 minus x squared. If you FOIL this out, we're going to get 25 minus 5x squared twice, plus x to the 4th. Combining like terms, 25 minus 10x squared plus x to the 4th. So that's what I'm going to plug in here. 25 minus 10x squared plus x to the 4th minus 1 dx. Let's clean this up. I mean, do yourself a favor. I see so many people, you know, finding an antiderivative, they get a 25x and then they get an x over here. Make your life easier. Clean that up first. I'll rewrite that as x to the 4th minus 10x squared plus 24 dx. Whew. Get out to the oxygen bottle, right? We're almost done. Now I need to integrate this. I'll take the pi out in front. What are my limits of integration here?
3 to 7.
Ooh, you got to be careful on that one.
2.
It looks like -2 to 2, doesn't it? It really looks like that. But is that really correct? Let's find out. So in order to find out, I need to find where these two curves intersect each other. How am I going to figure that out? Set them equal to each other. So let me see. Let me do that this way. I want to set y equal 3, so 3 equal to this. I want to know where their y heights are equal to each other. So 3 equals 7 minus x squared. So, well, I guess it does work out nice and even in this case. There was one that I used to have in my homework set that didn't. That's going to be x squared equals 4, so x equals plus or minus 2. So there was one where it worked out like the square root of 8 or something like that. It was really close, but visually misleading. All right, so we're in good shape here. -2 to 2 of this. This is a polynomial. I will let you do polynomials with the graphing calculator. I would suggest that you leave pi out of your calculation until you're all done. Now, even though it's just been today that I introduced this, I'm pretty sure that you're familiar with Math 9. And that's going to be your best friend here. -2 to 2 of x to the 4th minus 10x squared plus 24. And I kind of like you doing it this way because you're not going to end up with arithmetic errors. Now, there's probably one thing that I'm gonna ask you to do with this. Does anyone know what it is?
Fraction.
Turn it into a fraction. I do like fractions, I don't want decimals. So turn it into a fraction, we get 832 over 15. So we're okay there. But your final answer is not gonna be 832 over 15. What's it gonna be? 832 pi over 15. Now, just another reminder here. This is something that we saw the other day when we were working with integrands in chapter 5. When you see a symmetric interval, then you can get a little bit of savings here if this is an even function or if this is an odd function. If this was an odd function, what would the integral evaluate to? 0, if it's an odd function. Does this look like an odd function? No, it's an even function. And what you can do with an even function is you can calculate this as pi times the integral of 0 to 2, and we're going to double this and just do half the interval, x to the 4th minus 10x squared plus 24. Of course, this assumes that you recognize that that's an even function, but that would still give you the same integral here, or same number here. Let me see if I can't pull this one up. And I'll change my integration to be from 0 to 2. And I should end up with 416 over 15. Let's see that happens. Math, answer to fraction. There you go. So if you double it, you end up with exactly what we had in the first place. Let's try a couple more here. Do you want to practice? Yeah, maybe it's not a bad idea to practice what we just did, which is rotate around a different axis of rotation as opposed to the x or y axis. And we can do that in the form of example I. So let's look at example I next. This time we're going to rotate around the line y equals 1. So that's right here. Can you tell if this is going to be a disk or washer? Yeah, it's going to be a washer because this is not flush with your axis of rotation. It's just not. Another important question for you. Sasha, am I going to take a dx slice or a dy slice in doing this one? What would be perpendicular to the axis of rotation? A dx slice or a dy slice? Dx slice. Yeah. For the work that you're going to do in sections 6.2, it's always going to be perpendicular to the axis of rotation. So in this case, it's going to be a dx slice. So I'll sketch that in there. And that's going to result in a washer. So let me see, that's dx slice. I want to find the volume of one washer. So let me give myself a decent washer to look at. And so in the inner radius, I've got R1. In the outer radius, I've got R2. And the volume is going to be what it has been for the last couple problems, pi times R2 squared minus R1 squared times the thickness. And in this case, the thickness is my dx. So your job is to characterize R2 and R1 in terms of x. We know that it's in terms of x because I have a dx term right here. All right, so it's gonna be top minus bottom, but you're gonna have to think a little bit about how you're gonna set that up. All right.
We're not gonna rotate around a slanted line, if that's what you're asking. You can, but I'd probably affect that by a change of coordinates and then just rotate around the regular axis. So, yeah, there are substitutions you can make that affect a change of coordinates like that. CNC machines, I think, do stuff like that. They rotate things so that you can work on any axis that you want. But, yeah, we're not gonna do that. It's funny, some of that work used to be in aircraft class, but that was years ago. So start by finding your expressions for R1 and R2. It's gonna be top minus bottom.
I also see this on the spot as well. So.
For R2, would you?
Right, so then.
I got R2, 1 minus
So
X
x
squared.
equals y squared, which is the same thing as
And
y.
R1, I
X
got
would be
square root of X minus
r1. Let me actually try to write it down.
I'm not very sure. I thought it would be.
The top minus bottom has to be from 0 equals to 0 point to your axis of rotation. Your axis of rotation.
It's gonna be like this.
X squared minus 0 is 1 is top minus bottom. 2. That axis is the square root of 1 minus this, 1 minus that. And then everyone ratios.
Sure thing. I think you may be right though.
Keep in mind, you're rotating around the line y equals 1. You've got a different axis of rotation. It's gonna change your top and bottom functions.
It is. Y equals
Oh, I'm sorry.
Or it was minus 1. 1 minus X squared. It should be like.
Yeah, since he's saying because it's about this line, like if you were to flip it upside down and do it like this way, the top line,
And I think when you
I thought that
start,
was.
like you
I thought that
normally
was
get,
0.
the top line would be this one.
Yeah.
So,
Yeah,
it's supposed to be in
I thought
respect to the
0.
line, so I think this is the top one and that's the bottom one, even though it's like reversed.
So you
It should still be on the top. Yeah.
I have 1 minus X squared.
Top minus bottom.
Other way around.
It's just X squared. Top minus bottom, yeah. But top minus bottom, the other one's gonna be 1 minus X squared. Yeah, because there's your top, there's your bottom, bottom is X squared.
For R1, you got square root of X minus X squared.
For R1.
Yeah.
Top minus bottom. Top minus bottom. Okay, cool. Yeah, this one's gonna probably finish this off. Come here, maybe leave the pie out of it and see if you don't get 11 over 30.
Yeah, no, it's not a easy function.
This guy's a really tricky expert.
They're just trying to understand.
Yeah.
This hollow part on the inside, it'll touch into this. So this would
So let's kind of zoom in a little bit here for a minute. That's your inner radius, so that's R1. This is your outer radius, so that's R2. Remember, it's always top minus bottom. So in this case, it's going to be 1 minus this. Well, this one can't be the graph of y equals x squared. I know what that looks like. So this has to be the graph of the other function, which is x equals y squared. That's a sideways parabola. Or I could just take the square root on both sides. X equals, or square root of y, square root of x equals y. So that's this function. And it's okay to work with the positive root because I'm above the x-axis. So top minus bottom in this case, that's going to be my inner radius, 1 minus the square root of x. 1 minus the square root of x. How about over here? Well, 1 minus x squared. So there's my two radii. Let's put those into the formula over here. It's going to be pi times parentheses 1 minus x squared, squared again, minus 1 minus the square root of x squared dx. And at this point, we've got to square out these binomials. And it's not a bad idea if you know a particular formula. Let me put that formula up here. If you have a minus b and you squared it out, you're going to get a squared minus ab again plus b squared. Basically, you're boiling it out by multiplying it by itself. But if you notice, you get that middle term twice. So let's combine like terms, minus 2ab plus b squared. You're going to square out enough binomials in your math career that it's worth it just to be able to jump from here to here. The way I think of it as I do this is I know that the end terms are going to be squared, so I square those. And the middle term, for that, I borrow this 2. It's 2 times this times this. 2 times a times b, and the sign is going to be whatever sign is there. What's that going to look like here? 1 squared is 1, x squared squared is x to the 4th, and then 2 times this gives me a minus 2x squared in the middle. Minus. And I'll do the same thing here. And that is, I'll square this, I get a 1. I square this, I get an x. And the middle term is minus 2 square roots of x. Now, if you need to FOIL it out, if you need to do this times this in order to get that, that's fine. I understand. I'd rather see you get it right than get it wrong by being too proud to take an extra minute. If I distribute the negative sign, I get a minus 1 plus 2 square roots of x minus x dx. And unfortunately, you don't get a lot of simplification. What simplification do you get?
The one.
Yeah, the ones cancel. Like, ooh, big deal. Pi times x to the 4th minus 2x squared minus or plus 2 times x to the 1/2 minus x dx. Whew. A lot of work to get there. Let me pause for a second, let you catch up. See if maybe I went a little too fast on something, you wanna revisit it. Are we okay with the expression that's gonna become part of our integrand? Nick, is that looking okay? All right, so I'm gonna integrate, take the pi out in front, x to the fourth minus 2x squared plus 2x to the 1/2 minus x dx. Mason, was I right that this part turns into 11/30?
Yeah.
Okay. I need to set up my limits of integration. Now, if you look carefully at your graph, you can kind of see what those limits of integration have to be. You're gonna start here at 0 and go all the way up to 1 along the x-axis. That's as far left and as far right as you can take slices in this region. So let's put those limits in there, 0 to 1. I'm not gonna go through all the horrific work in doing this by hand. You're just gonna end up with pi times 11/30 when you do this one. So your final answer would be 11 pi over 30. Whew. How's that one looking? Better? Yes, somewhat. Let's get back to a saner world. Now, you can probably reasonably expect a couple of different levels of difficulty from me on the exams. There's a lot of choices I have in terms of problems. Rotating around a different axis, rotating around the y-axis, so it forces you to take a dy slice, getting a washer as opposed to a disc. But let's go back and practice one on the easier side of things, which would be a disc method. And that disc method is going to help us figure out kind of an interesting formula, something that you've probably used, more than once. But last chance. Anything here that isn't quite clear? Something else I can help out? Yeah, Joshua, please.
I got the integrand and everything, and I put it in my calculator, wasn't able to get 11/30.
Same.
Same?
I got like point, it had like a bunch of random numbers.
You get point.
Like 3, 6, 6, 6, 6, 6, 6, something.
Okay.
R1 and R2 are flipped.
It's like close to it, but it's not.
Let's see. R1.
Like, and when I tried to go
Oh.
through it individually, it had a problem with when I did the 2x to the 1/2. That's what it had the problem with.
2x to the 1/2.
Or if I put it in as 2 root x.
2 root x. And it should take it either way.
I guess.
Let's see here. Somebody said I had R2 and R1 flipped. Let me check back at that. R1, R2. R2 would be the outer radius, so that'd be 1 minus x squared. So I'm sticking with, that's my R2. That looks good, that looks good. Are we in agreement with the integrand? Does the integrand look okay?
I would have thought that R1, like if you flipped it, if we're going about this way, then R1 should have been.
R1's gonna be the smaller radius. It's gonna be what's closest to your axis of rotation. R2 is gonna be the farther away point, and that's gonna come between 1 and x squared, whereas 1 and the square root, that's gonna be your inner radius. So R2 is gonna be 1 minus x squared, I agree with that, and 1 minus square root of x, I agree with that. So I'm sticking with R1 and R2 as they are. Let's check this out in terms of numerical integration. So I think I just,
It's right on the calculator.
does it say you get 11
Yeah, I got 11.
over 30?
Yeah.
Okay. Let me just check it just for grins. So let me clear out this stuff here, and this stuff here. So math 9, your new favorite little spot here on your calculator, 0 to 1 of x to the 4th minus 2x squared plus 2x to the 1/2, so 2x raised to the 0.5 power minus x. And that's dx. Math. All right, so what's happening is that this value is not 100% accurate. I think those 6's should continue. But let's just try 11 divided by 30 and see how that compares. Oh, looks pretty good. So, yeah. Now, if you keep in mind, I did say we could use this numerical integration for polynomials. Technically, that's not a polynomial because you have an exponent that's other than an integer, but I'll be really careful not to give you something that's so drawn out. I don't want you to spend 10 minutes trying to simplify something like that. To me, most of the points on this problem are going to be setting it up, getting the proper integrand, etc. You know, the final answer, yeah, that's worth a couple points, but it's not going to be everything for the problem. Audrey?
When you do it algebraically, it does come out to 11 pi over 30.
Yeah, I'm sure it does. It's just that I don't want to take the time now. Yeah, thank you. Leif?
How come some calculators do it with like 0.36 repeating, but other ones do it like that, it's like 7?
I've got an older operating system on my TI SmartView, so that might be part of it. I'm not sure which one. Well, yours is doing it with direct algebraic logic, so that's different than what, say, Joshua's is doing. Joshua, what does yours do? Is yours more like mine? Okay, yeah. So the TI-89 can work things a little bit differently. So it's probably giving you an exact answer as opposed to this calculator, which is doing an approximation. That's the very last thing we're going to cover after the test on Tuesday is, you know, how do you do this when you can't find an antiderivative? There's a lot of famous problems that just don't have an antiderivative. In particular, one that's used in statistics all the time, which would be, you know, the area underneath this curve. From, say, negative infinity to some number a. There's just not an antiderivative for this. And yet we need to find that area. It's part of what's called the normal curve, or also called the Gaussian. It comes up in statistics like everywhere. So at that point, you need some numerical methods, and you'll get a taste of that coming up. Let's go back and do a historical problem that I mentioned at the start of this class. Is I'm going to take, I don't know, this figure here. What's that look like? Yeah, half circle, a semicircle. And I'm going to give it a nice general equation. We'll call it x squared plus y squared equals a squared. All right, so if I do that, then the x-intercept is going to be at a and negative a. So, all right, looking good there. And I'm going to rotate this around the x-axis. Now, what's going to happen when you rotate a semicircle around the x-axis? What kind of volume is that going to trace out? Somebody said it. A sphere. It's going to trace out a sphere. So basically, we're going to figure out how to be able to find the volume of a basketball. So let's play around with that. If I'm going to rotate this around the x-axis, Joey, what kind of a slice do I need to take? Dx or dy? Dx. Perpendicular to our axis of rotation, so looking good there. Lillian, when I rotate this around the x-axis and take my slice like this, am I going to end up with a disc or washer? What kind of a figure is this little thing going to trace out? A disc or washer?
Disc.
A disc, yeah. This whole figure is flush with respect to my axis of rotation. So I want to find the volume of one disc. Thank you. Volume of one disc. So, okay, well, let's think here. Volume of one disk. Let's draw ourselves a little disk here. All right, so a really homely looking disk, but hey, no judgment, right? R. The volume is going to be the thickness, which is dx, times pi r squared. Pi r squared dx. That dx is screaming out to you, okay, we need to figure out what the radius is in terms of x. Thank you. So let's figure out what the radius is. Let me squeeze that in here. Radius. Well, the radius, as before, is going to be the top minus the bottom. And I don't know exactly what that point is. We'll just call it, say, x and y. And you could do top minus bottom as, well, y minus 0. But that doesn't exactly help you because we need to have things in terms of x. So now is where we got to slow down a little bit and think. How am I going to get this in terms of x? What can I replace y with? Well, let's see. I could move the x squared over there and get y squared equals a squared minus x squared. That's kind of close to what I need. It's not quite there. How's
Replace the y with an r.
how do you solve for y? Take the square root. So y is going to be the square root of a squared minus x squared. Please don't simplify that as a minus x. That's not what it is. You can't distribute the square root to that like that. So this is the square root of a squared minus x squared. I'll forget the minus 0 because it's not going to change anything. If I plug that in to my expression here, the volume of one sphere is going to be the square root of a squared minus x squared squared times dx. And when I square that, I just get pi times a squared minus x squared dx. And that's looking pretty friendly. So that's what we're going to integrate. We're going to integrate, now we'll factor out the pi, a squared minus x squared dx. Okay, looking good. Audrey, what should be our limits of integration?
0 to
Where can this slice be taken and still remain within the pink pink circle?
It's negative a to a, sorry.
There you go, negative a to a, negative a to a. Does someone notice anything about this integral that might be helpful?
It's symmetrical.
It's a symmetric interval, so you start looking at the integrand and saying, all right, well, what's going on with the integrand? Now keep in mind that a is just a constant. It's just some number. We don't know what it is, but it's just a number. Call it a parameter if you'd like. X squared is an even function. A squared minus x squared, that's an even function. So we can save ourselves a little bit of work by, instead of going from negative a to a, I can go from 0 to a, but double this. So 2 pi times a squared minus x squared dx. Okay. Here's the tricky part. 0 to a. I need some antiderivatives. I know that you can give me the antiderivative for this one, that's x cubed over 3. But what's going to be the antiderivative of a squared? Ooh, somebody got it pretty quickly. I'm not sure if everyone heard you though.
A squared x.
A squared x. This is just a number. What do you differentiate to get that number? Well, a squared times x to the first power. Nice. So let's see, that's gonna be 2 pi times, well, let's plug in the upper limit there. So it's gonna be a squared times a minus a cubed over 3 minus, well, at the lower limit, it's just gonna be 0. So we'll end up with 2 pi times a cubed minus a cubed over 3. If you get common denominators, you'll end up with 2a cubed over 3 minus 0. If I distribute the 2 pi to this term on the inside, well, actually even both of them, I'll end up with 4 pi a cubed over 3. Does anyone recognize this formula? The volume of a sphere. You put in an r there and it might look a little bit more familiar. 4 pi r cubed over 3. That's the formula for the volume of a sphere. And Archimedes did that 2,000 years before Newton invented calculus. Brilliant.
Any derivatives?
No, he just did it strictly geometrically. That much I know about his proof. I don't know it intimately, but I do know that he just used geometric arguments. So, pretty brilliant. All right, how are we looking on that one? Guys, all set for these types of problems? You want to do one more? Yeah, no. Yeah, you guys, students are a unique kind of consumer group. You guys don't want your money worth. No, that's enough, that's all right. No, you don't need to sign extra homework. No, I don't want to know what's all in the book. No, it's okay. I'm gonna go into McDonald's and order a quarter pounder and settle for a 10th pound hamburger, you know? So anyways, all right. Let me put this one to rest and talk about what's coming up.